all the chapters we have done so far have really been leading up to this point. Inferential statistics, which, if under a given assumption, the probability of a particular observed event is extremely small, we're going to include that the assumption is probably not correct. If it's unlikely to happen, we're not saying it's impossible, we're just saying that it's probably not true. So, we make a hypothesis. There are two kinds. The first is called the null hypothesis. This is a statement that the value of a population parameter, a proportion, a mean, a standard deviation, is equal to some claimed value. Null is used to indicate that there has been no change, no effect, no difference. So imagine, for example, that you are taking a drug, and the question is the drug, does it work? The null hypothesis would say it doesn't work, it doesn't do anything at all. We test the null hypothesis directly by assuming it is true, and then reach a conclusion to either reject or fail to reject the null hypothesis. Please note, we do not prove anything in inferential statistics. We basically say we have enough evidence to reject, because it's extremely unlikely it's going to happen, or we fail to reject, basically saying we don't have enough evidence to say that it couldn't happen just the way it did. Our other hypothesis is called the alternative hypothesis. Sometimes you'll see this written as H1, and other times you'll see it written as HA, A for alternative. This is a statement that the parameter has a value that differs from the null hypothesis. For example, we might say that P is greater than 0.5, or P is less than 0.5, and these are different from the one in which we were saying P is equal to 0.5. We might even say that P is not equal to 0.5. Any of those particular alternative hypotheses to the one that's listed here would be examples of alternative hypothesis. If you are conducting a study and want to use a hypothesis test to support your claim, the claim must be worded so that it becomes the alternative hypothesis. You can't support a claim that some parameter is equal to some specified value. You just reject it or fail to reject it. The alternative hypothesis is sometimes referred to as the research hypothesis. Now, there are some steps, if you will, for your hypotheses. First off, you need to identify the claim to be tested and express it in symbolic form. You need to give the symbolic form that must be true when the original claim is false. So, for example, if you had one like P is greater than 0.5, then the opposite would be that P is less than or equal to 0.5. H1 is the symbolic expression that does not contain the equality. H0, when we have a little zero, we call it not. H0 is the symbolic expression that the parameter equals the fixed value being considered. The original claim may or may not be one of the above two symbolic expressions. It just depends on how things are worded. Alright, so we have our test statistic. We went over those in the previous chapter, chapter 6. Okay, we have z-scores for proportions. We have z-scores or t-scores when we're dealing with mean. The difference is, do we know the standard deviation or do we not know the standard deviation for the population? And then we have the chi-square scores for variance and standard deviation. So, a critical region or rejection region is the set of all values of the test statistic that causes us to reject the null hypothesis. such as the region or area to the right of a critical value. So these are finding critical values. And again, think in terms of our normal distribution. Things on the outside are less likely to happen. Things in the middle are more likely to happen. So if it's on the outside, if it's beyond these test statistics, the critical region, then we can inferentially say that it's unlikely to be true. Okay, we've talked about significance level before. That's the probability that the test statistic will fall in the critical region when the null hypothesis is actually true. If the test statistic falls in the critical region, we will reject the null hypothesis. So alpha is the probability of making the mistake of rejecting the null hypothesis when it's true. P-value. The p-value is the probability of getting a value of the test statistic. So basically we're going to find our test statistic. Then we're going to find the area associated with that test statistic under the standard normal curve, and then compare that with alpha. The probability of getting a value of the test statistic that is at least as extreme as the one representing the sample data, assuming again that the null hypothesis is true. The null hypothesis is rejected if the p-value is very small when compared to alpha. So again, if p is low, the null must go. If the p is high, if it's bigger than alpha, the null will fly. We fail to reject H0. And then to kind of finish up some of the vocabulary for the section, types of hypothesis tests. We have two-tailed tests, which means the rejection regions are in the two extremes, the two tails of the curve. Again, think of a standard normal curve. The rejections are in both extremes. A left-tailed test, which would be related to p is less than some value, if you're doing proportions. And the critical region is in the extreme left region in that case. Or a right-tailed test, that would go with p is greater than some value, and that would be the critical region in the extreme right region under that curve. There are specified errors in hypothesis testing. A type 1 error is the mistake of rejecting the null hypothesis when it's actually true. A type 2 error is the mistake of failing to reject the null hypothesis when it is actually false. So you could think of these as like false positives and false negatives. Power is the probability, labeled 1 minus beta, of rejecting a false null hypothesis. The value of the power is computed by using a particular significance level alpha and a particular value of the population parameter that is an alternative to the value assumed to be true. Just as 0.05 is a common choice for a significance level, a power of at least 0.8 or 80% is a common requirement for determining that a hypothesis test is effective. Now, if you look in the book, it will say that estimating the power can be quite difficult, and in reality, we're not going to do any problems in which we have to estimate the power. It's just, it is used, and you will sometimes see it referred in hypothesis testing to the effectiveness of your test. All right, so let's now look at some examples of these different terms. So we're going to go through most of these terms with this one situation. Among 14 couples using the XORT gender selection method, 13 couples had girls and 1 couple had a boy. So how could the claim that the XORT method is effective be symbolically written? Well, if the method had no effect, what's the probability of having a boy or a girl? It's 50-50. So the proportion here, P, would just be 0.5, if the method had no effect. On the other hand, how could we symbolically write the claim that the XOR method is effective? Well, effective means it increased the chance of having a girl, and so P is greater than 0.5. And please note that most of the time our claims are going to be, in a sense, that general. You know, we're not going to worry about is it really 0.5 or 0.6 or 0.8. It's just, hey, probability would say 50-50. We're improving on the 50-50 case, so greater than 0.5. All right, let us assume a normal distribution. Find the probability that we would have 13 or more girls. Now, this is a binomial type situation, so mu equals NP and sigma equals the square root of NPQ. For x, we are actually going to use x subtract 0.5. We do that. That's a correction factor to make sure that we include the case of 13 and or more. If we left it there, we would just have greater than 13. So we need to do this little correction factor to make sure that we include the minimum case. Now, we want to find z and find the area. So again, this is a binomial case. N is 14, P is 0.5, Q is 0.5. This would be normal, 50-50 chance, boys or girls. So what is the probability that we would get 13 out of 14 girls? So notice x is 13. We make our correction factors. So we're actually going to look at 12.5, which will make sure that we include the 13. Mu is NP, which is 14 times 0.5, which is 7. Sigma is the square root of NPQ, which is 1.87. Now I can go find my z-score. Remember that z-score is the value, subtract the mean, divided by the standard deviation. And so plugging those numbers in, our z-score comes out to be 2.94. We use table 4. We look up the area, 0.9984. Remember that the standard normal distribution table always gives you values to the left. Okay, but we want the more than case, so we actually want to the right. So we have to subtract from 1. That tells us that the area to the right of this z-score, okay, so this area is to the right of that z-score, is only 0.0016. So the probability of having 13 or more girls is 0.0016. Now, considering the result in part B, is it likely the 13 girls is due to random chance? Well, 0.0016 is really small. If we use our 5% rule, it's way smaller than 5%, so it's very unlikely. Not impossible, but very unlikely. All right, now write a null hypothesis and an alternative hypothesis for the claim that the XOR method works. So, first, the null hypothesis. Again, we label it H0. We're doing proportion here, the number of girls out of the total number of babies that were born. The null hypothesis, the XOR method, is not effective, just random chance. Well, the chances of having a boy or girl are 50-50. So the null hypothesis matches reality. On the other hand, the alternative hypothesis, the claim is that the XOR method actually increases the chance of having a girl, and so instead of being 50-50, it's better than 50-50. It's greater than 0.5. All right, now, assuming that the null hypothesis is true, find the test statistic for the proportion. Okay, so first off, now in some problems they will give you p-hat. P-hat is the proportion for your sample. In this case, our sample is 13 out of 14, which when you do the division gives you 0.929. Sometimes they'll just give you that, but sometimes they will give you the two numbers, and so you have to do this division to get your p-hat. P is 0.5. Again, that goes back to the null hypothesis, so that when we then plug it into our equation, our test statistic equation, for the z-score. And again, just to remind, there is a separate one depending on whether you're doing proportion, mean, or standard deviation. So we're using the one for proportion here. P hat minus P over the square root of PQ over N. We plug in all our numbers. We get a z-score that is 3.21. The table has 2 decimal places for its z-score, so we'll always round to the second decimal place. So there is our test statistic for 13 out of 14. So, using a significance level of 0.05 for alpha, find the critical z value for the alternative hypothesis. So again, this critical value is based on alpha. So if we have 0.05 in the right tail because of the greater than case, but remember the table 4, standard normal distribution, only goes to the left, so we're not going to look up 0.05, we're going to look up 0.95 within the table to find out what z-score matches the 0.95. So again, for the greater than case, the alpha is in the right tail. It's on the extreme. We don't want to the right, we need to the left, because that's what the table is. It's always area to the left. So we have to subtract from 1 to get 0.95. When we look up an area of 0.95 within table 4, that tells us the z-score, which is the critical z-score value, is 1.645. By the way, if this had been p is less than 0.5 instead of greater than, then the alpha would have been 0.05 in the left tail. We wouldn't need to do this. We would just look up 0.05 in the left tail, which would, by the way, would still be 1.645, but now the z-score would be negative 1.645 because it's in the left tail. Alright, so determine whether the given conditions result in a critical region in the right tail, left tail, or 2 tails. So this is not referring to what was above. We just want to look at these cases and decide what's going on. And so the claim is P is greater than 0.5, so that means the critical region is in the right tail. If we were using the test statistic, 3.21, so we're not doing what we just did up there. We're using this 3.21. That was the test statistic that we had just found. Let me go back to the previous page. Okay, so here's what we're doing. We're using that test statistic. It corresponds to an area of 0.9993 to the left. Again, our critical region is in the right tail. So subtract 0.9993 gives us 0.0007 in the right tail. This is the p-value. Little note, if we were doing a 2-tailed test, our p-value would be 2 times the left or right area. Since we just have a greater than, or if we had a less than, whatever we get for that area, that was our p-value. Okay, next, assume using the XOR method the likelihood of having a girl is not equal to 0.5. Find the p-value. Okay, so if we're not saying p equals 0.5, but we want to use p does not equal 0.5, that would make the critical region in 2 tails instead of 1. Again, anytime you have not equal to for your claim, then it's 2 tails. Anytime you have greater than or less than for your claim, then it's 1 tail. Greater than will go in the right tail, less than will go in the left tail, not equal to 2 tails. So, using the same thing we just did, note that the 0.0007 gets doubled because now we're thinking about the area in both tails. Alright. How would we think about type 1 and type 2 errors? We want to give some statements. So our hypotheses in this problem were that p equals 0.5 for the null hypothesis. The XOR method made no difference. And the alternative, hey, p is greater than 0.5, the XOR method did make a difference. So the type 1 error could be restated as, there is sufficient evidence to support that p is greater than 0.5. That's what our sample led us to believe, led us to infer, but in reality, it didn't do anything. P is still 0.5. 50-50 chance of having a girl. Type 2 error, opposite kind of idea. There is insufficient evidence to support that p is greater than 0.5, when in fact it really is. So in this case, we would have failed to reject the null hypothesis. Okay, insufficient evidence to support it, so we can't reject the null hypothesis that there's no difference, but in truth there was a difference. It's just our one sample. And that's part of the idea here. We have one sample. We have one test statistic from a sample that we're inferring, that we're generalizing to the entire population. And so our one sample may not be sufficient to support evidence to fail to reject the null hypothesis or to reject the null hypothesis, because it's just one sample. And so we can have these type 1 and type 2 errors. Alright, so now we're going to move to some other examples. Let's suppose that we want to find the null hypothesis, H0 and H1, in the symbolic form for, here's our claim, the majority of college students have credit cards. So, notice alternative goes with the claim. P greater than 0.5, that would be the majority. Notice the null hypothesis goes with equals to. Now in the book will tend to write this as the counterclaim. So if you have greater than, over here you'll have less than or equal to. In other places I have seen it just made an equal to. It really doesn't matter about the less than point, because it's not that. So equal sign with the null hypothesis regardless of what's over here. Alright, second example. The standard deviation of daily rainfall amounts in San Francisco is 0.66. So note, the actual claim is a particular number. It's not greater than or less than. So the alternative becomes a not equal to. And the reason it becomes a not equal to is the null hypothesis always has to get the equal sign. Which means the counterclaim, the claim itself, we have to go with the not equal to. So the alternative hypothesis will not always match the claim. And again, even though it doesn't have the word claim in there, that's what this is. This is a claim that the standard deviation of daily rainfall amounts in San Francisco is 0.66. And then basically we would get a sample of a certain number of days and then try to decide, did it match the claim or not, or was the claim believable or not. Alright, we now want to assume a normal distribution, and we're going to practice finding the critical z-values based on the information provided. So first off, we know it's a two-tailed test and our alpha is 0.1. Now go ahead and just put this up so you can see it all at once. So if it's two-tailed but alpha is 0.1, then that means it's 0.05 in both tails. 0.05, 0.05 gives us the 0.1. If you look up 0.05 in table 4, you get the negative 1.645. If you subtract 0.05 from 1, you get 0.95, which gives you the positive 1.645. Two-tailed should always have a plus or minus. Okay, left-tailed. Alpha is 0.1, so the 0.1 is in the left tail. Well, a 0.1 area in the table gives us a z-score of negative 1.28, or at least that's the accompanying z-score for that area. Alright, now I'm told alpha again, but I'm given the alternative hypothesis. And then I have to interpret, hey, is this one tail, two tail, left tail, right tail? What is it? Well, this is P is greater than 0.5. Okay, so that means it's one-tailed. Okay, now, if alpha is 0.001, then we are looking for 0.99 to the left. And you're like, well, wait a minute, this match, yes. Okay, it did match. When it was left tail, it matched. Okay, but when it was two tails, we had to do both of them. Here, I had to do 1 subtract 0.001 to get 0.99. Look up 0.99, it gives me 2.33. If you look up 0.01, you're going to get negative 2.33. Okay, last example, P does not equal 45. Just like we had earlier, if you see a not equal, that means two tails. So we take our alpha, we split it into the two tails, 0.005 becomes 0.0025. If you look up 0.0025, you get the negative 2.81. If you say 1 subtract the 0.0025, you get 0.9975, which gives me a positive 2.81. Again, the not equal to's will always give you positive and negative. So that's section 1. Just kind of setting us up for things that we'll do in the rest of the chapter.